Hi, I'm Matt Stine. I'm going to say a few words about resilient architectures. If you want to interact with me, probably one of the easier places to do that is on Twitter. If you're looking for me to say profound professional things, that's probably not the place to get that from me. I mainly use Twitter to amuse myself. If you want to kind of see the stuff that I've written and other talks that I've given, my website's kind of useful for that. So diving right in, I want to start out by looking at some anonymized recent technology headlines. You may have experienced one or more of these. Maybe even in a crowd this big, there's somebody who was a part of one of these. I'm not trying to shame anybody. Let's just get that out there. The point is to draw awareness to the problems that we're actually trying to solve. So, system failure cost a well-known retailer significant revenue on the biggest internet shopping day of the year. This has happened several times in the last 2 or 3 years. Retailers make all of their money in a very short period of time. And in that short period of time, that's when their systems are put under the most stress. And when they fail, and when they fail spectacularly, then you don't make that money. And that's a big deal because you usually don't have another opportunity to catch up until a year later. This one is near and dear to my heart because of my lifestyle. System failure causes cancellation of hundreds of flights, stranding thousands of airline passengers, ultimately costing the airline millions in revenue. If you're familiar at all with the way airline travel works, you know that if you lose even a few flights, that not only strands passengers, but it also puts planes out of position. And so actually recovering from those misplaced planes and recovering from those misplaced passengers has a cascading effect where a few hours or a day of problems can lead to weeks of recovery. And once again, a lot of money is lost in that equation. Beautifully designed online store crumbles under the pressure of a thundering herd of customers trying to purchase the latest tech gadget. I used to stay up until 3 o'clock in the morning to buy iPhones. I don't do that anymore. I'm not nearly as excited about it as I once was. But myself and actually another speaker who's speaking against me right now, we did that one year, and we're texting at 3 o'clock in the morning, hey, have you gotten in yet? No, I haven't gotten, going back and forth, and about 5 minutes after the iPhone that we were buying that year went on sale, basically every site that sold the phone was down. And this was several generations in, but obviously they recovered from that fairly quickly. But again, people who are trying to get in, the store can be great. It can work really great for a normal load of customers, but can it handle that kind of a spike, even if it's planned? And then you've got security breaches, customer credit card numbers, other personal information, again, leading to millions in lost revenue due to, in this case, resulting loss of trust. So a lot of the focus today, like what we're trying to learn as an industry, is on IT's lack of speed. How can we go faster? How can we be more agile? How can we be more productive? But it sounds like even when we're going slow, we struggle to keep systems resilient. So how can we do it going faster? Well, this actually requires a fundamentally different approach. And if you think about the approach that we've had up to this point, usually it's about mistake prevention. So if we just do a little bit more testing, if we just do a little bit more release engineering, if we have a few more reviews, if we have a few more approval processes, then we'll be able to prevent things from happening. And the problem is we don't prevent things from happening. And then we create this process that's pretty heavyweight and makes it kind of hard to get changes into production. And so when things break, we don't actually have time to execute our process so that we can fix those breakages. And so we end up fixing the problems outside of the process. And so we end up doing break-fix work sometimes in the production environment, and sometimes those changes never make it back into the real process, and that makes resiliency even harder, and we create more problems. And so we kind of have this chaotic cycle that kind of feeds back on itself. So what a lot of these disruptive companies are doing is saying, well, it doesn't seem to work to try to prevent mistakes. Doesn't matter how much work we do, we don't seem to be getting any better at it. In some cases, we get worse. So maybe we should just stop trying. Maybe we should just embrace the fact that failure is going to occur. We know it's going to happen. And in fact, as we'll see a little bit later on, sometimes we might make it happen intentionally. And let's make it really cheap to recover from failure. So we start to think about, well, how do we measure success? Well, the way we've measured success in many ways traditionally is MTBF, mean time between failure. We want that number to be really big. This is actually a metric that we borrowed from the manufacturing industry. I grew up, driving past my father's manufacturing plant that he worked at, and there's a big sign out front that says, number of days since this plant has had a safety accident. And they're really proud that that number is really, really huge. And if anytime somebody got hurt, that clock went back to 0. And that was not a happy event. And so we kind of translated that metric into software, but maybe it's not the best metric to measure success in this case. So we're kind of moving in this direction of MTTR, mean time to recovery. It doesn't matter how many times we fail, mean time between failure can be really small, but as long as mean time to recovery is also really small, then maybe we can actually recover so fast that our users don't experience it. Now, if we want to work this way, we really need, I say better, maybe different tools and different techniques. And ultimately, we need the architecture to give them to us. Like, we can't just assume that we're going to go build a bunch of software the way we've always been building software and throw it into production, and we're somehow going to magically be able to depend on an operations team to make all this stuff happen. We actually need to build the software differently. And so that's where we're going to get into talking about this notion of resilient architectures. Now, I really just want to tell you 3 basic things about that. What do resilient architectures do? The first thing is that they enhance observability. What is observability? It's our ability to see into what the software is doing. We can't tell if the software is sick. We can't tell if the software is recovered if we don't have the ability to see. Resilient architectures also leverage resiliency patterns. The interesting thing about a lot of the problems that we're going to run into is they're pretty well understood. We talk a lot about microservices and distributed architectures right now. We've been doing distributed systems research for a really long time. If you want to figure out how to build distributed systems well, don't go read a bunch of blogs, go read a bunch of peer-reviewed papers, and you'll actually learn everything that you need to know. And a lot of the solution patterns already exist. We just need to learn them and leverage them, and I'll talk about a few of those. And then we need to embrace chaos. We need to get to the point where our architecture assumes that it's always going to be under some sort of an attack. And we'll break down exactly what that means when we get there. So let's dive into enhancing observability. Spend a lot of time talking to teams about architecture. And they tell me, we want the architecture to be highly available. And I just kind of come right back with a question, saying, what does that mean? Like, highly available, how do you measure highly available? we actually have to understand our resiliency requirements much more resiliently than that. Like this idea that, oh, well, the system should never go down. The system's going to go down. The question is, what do we want to happen? How do we want to recover from that? Has anybody read the Site Reliability Engineering book from Google? Anybody? I can hardly see any of you anyway, so it doesn't really matter if you wave. If you haven't read this book, you don't necessarily need to read all of it. This book is about basically how Google runs Google. And a lot of the stuff in the book is very specific to them. But there are some chapters in the section about principles that are really, really helpful. Really, chapters 3, 4, and 5 are where you need to focus. And you can read this online for free, so Google's published it on a public website, so you can go read it without spending any money, and it's really worth your time. And so one of the things that they focus on is measurements, and what types of measurements do we need to have, and how do we need to work with them. And they divide it up into basically 3 different categories. So the first thing that we look at is this notion of a service level indicator. And this is some quantitative measure of a level of service that we're providing. So you might look at something like request latency. What is that over some window of time, over some cluster of servers? Give me a measurement of that. But this is not enough. Just knowing, hey, I can look at, here's the numbers for request latency, doesn't really tell me much, because I have to think about, all right, well, what is acceptable request latency? What is normal request latency? And what is unacceptable request latency? What is abnormal request latency? And so for that, we need to design the focus here, which is a service level objective. This is our target value or range of values for a service level as measured by a specific SLI. So we come back to request latency, we might think about, okay, request latency should be between, say, 150 milliseconds and 750 milliseconds over a period that we measure. And so then we have the ability to say, for each of these service level objectives, what's acceptable, what's normal, what's unacceptable, what's abnormal, and we can watch these service level indicators to tell us, hey, are we meeting our objectives or are we not meeting our objectives? Now we can take these and we can transform them into the thing that everybody talks about, which is service level agreements, SLAs. We talk about SLAs and not a lot, but probably most of us aren't actually doing SLAs because SLAs actually have consequences associated with them based on some contract. So, if I don't meet this objective, then I have some financial penalty or some other penalty associated with it. I might have a contract with a customer that says, hey, if I don't meet my SLA, then you don't have to pay me as much money this month. So we need to have the foundation laid before we can actually do that well. Another thing that's important is to focus on distributions. We talk about mean, average a lot. Turns out to be not that useful most of the time. It's entirely possible for a lot of your requests to be really, really fast. But at the same time, there's this long tail of requests that turns out to be really, really slow. And so this is a graph that I actually yanked right out of the SRE book. And if you look at it, you can tell that, well, for a typical request, we're actually serving that up in about 50 milliseconds. But 5% of the requests are as much as 20 times slower. If we just look at the average, that purple line around 50, We see maybe a slight increase, but really not so much detectable. Seems like things are mostly the same all the time. If we start to get up into these higher percentile buckets, we see that we go from a mostly even set of performance to a really jagged and spiky set of performance. And if we're just looking at the mean, we can't even actually see that. Now, we have to start to think about, well, which of these is more important? Is the average what our users are experiencing, or is it our 90th and 95th and 99th percentile? Which one of those is more reflective of the normal experience? There's a really great blog post out there that you can go read. In fact, if I tell you to read something, please go read it. It's worth your time. I don't have much time to read, and so when I say read something, this is like, go do it tomorrow. It'll be worth your time. This is a fantastic blog post because most of us actually don't understand how latency works. I didn't understand how latency worked until I really started diving into it. And this summarizes a lot of the really interesting problems. And it's cleverly titled, well, everything that you know about latency is wrong. There's this really nice table that summarizes a bunch of popular web pages that people go to and asks the question, well, how many visits to these web pages is actually going to experience a 99th percentile latency? So you can take the number of requests generated, so in this case Amazon.com, you visit Amazon.com, that's going to cause 190 requests to actually get fired off in one visit. And then we can do a calculation that says, well, of those 190 requests, how many are going to experience a 99% latency? And then we can come up with the chance that what percentage of visits will have that inside of it. And so for Amazon.com, 85.2% of the requests to that website are going to experience a 99% latency. You go to the bottom of the table, even Google.com, which is what? A text field and two buttons. 26.7% of requests to that page are going to experience a 99% latency. What that tells me is that anywhere between 25% and 90% of my users, depending upon how my site's architected, are going to experience, quote unquote, the worst case latency, not the average case latency. And so worst case latency turns out to be much more indicative of what our users are experiencing. If you go back to the Google SRE book, they talk about how a lot of teams at Google don't even think about averages. They optimize for 99% latency with the assumption that if the 99% latency is good, well, the average latency is probably going to be pretty good as well. So we need to measure a bunch of things. Maybe we're not used to measuring things. How do we get started? Google talks about 4 golden signals that if you don't know where to start, here's a good place to go. And we've already talked about one of them, latency. We want to have a way to measure things so that we don't find out that the website is slow by a user picking up the phone and saying, the website's slow. We don't like those phone calls because they're really hard to figure out, okay, well, exactly what do you mean by slow? Sometimes that slow can actually be normal. Sometimes that slow is abnormal, and we don't necessarily know which one it is. We want to measure traffic. So here's our latency right now. Here's how much demand is on the system right now. And that can start to tell us, well, under what conditions is latency acceptable? How much traffic can we actually handle? We probably have some notion of acceptable error rate. So depending upon what type of load the system's under, what's actually going on, we're going to probably have some proportion of requests that are in the 200s and some are in the 500s. Saying, I'm never going to see an error. Also, again, not going to happen. So how many errors are acceptable? And then a really interesting one, which is called saturation. Every system has a tipping point. You can't design any system, any architecture that's going to work under all circumstances relative to load and relative to what is the bottleneck for that system. So in some cases you're memory constrained, in some cases you are I/O constrained, CPU constrained, whatever. You need to understand how full is your service right now. If you hit that tipping point, all of these other measurements are going to go out of whack. And a lot of systems actually degrade in performance way before they ever get to 100% utilization. And so we actually want to have a utilization target. We want to understand, how much traffic are we going after? And if we're going after a substantially larger amount of traffic, then we may need to scale the system, we may need to re-architect the system. So how do we measure these things once we know what we're going to measure? Well, we want the architecture to give us different types of telemetry. And so I've got two different categories here. One is service telemetry, one is integration telemetry. So, I want to know traceability. I want to know when I'm looking at a process, what is that process? What code in Git represents that process? What package coordinates in Maven? What API version are we serving up? What features are toggled on or off right now? I want to be able to measure health. What is my health? Am I healthy because of what? Is it the process is up and running? Is it the process is up and running and it's listening on a port? Some of those things may be healthy, some of those things may not be. This can get complicated. And sometimes my health can actually be based on my dependencies. Microservices aren't going to necessarily save us from health problems. In fact, they might create health problems. And so we have to think about, well, what are our critical dependencies? What are our required dependencies? And if those are unavailable, can we actually do work? We talked about quantitative measurements. We talked a lot about technical metrics, latency, traffic, error rates, but there's also business metrics. How many shopping carts are completed? How many shopping carts are abandoned? How many signups do we have? Things like that. Those are also important. And then qualitative measurements, things that we want to know about, but that we can't actually attach numbers to. So this is kind of where we get into our logging. And then we need to start to measure for a distributed system what's actually going on in the system as the behavior emerges from all of these nodes communicating. We're going to talk about circuit breakers a little bit later. If we're using those, circuit breakers can actually help us to measure what is the behavior at the edge, what is the health at the edge of a graph. Distributed tracing. Request comes in, it's going to flow through a huge distributed system. Who's contributing to the latency? Can we actually isolate a system-level latency problem down to a specific component? If we're using messaging, using the measurements of our middleware like Rabbit or Kafka to understand what's going on there, and then taking our logs also and actually correlating those. Now, I'm going to show you some examples, of how we do this in the tech stack at Pivotal. A lot of folks using Spring Boot. Spring Boot has created a really nice set of features in what's called the Actuator that allows me to, out of the box, have a lot of this telemetry just work. So one of the really cool things is the health endpoint, that as I add more dependencies to my application that are interacting with different things, each of those dependencies, whether it's Spring Data or Spring Security or any of the other projects, can actually bring health indicators along with them. And then the health indicator subsystem is going to aggregate all those components to give you an understanding of, well, what is the health of this particular service? And then I can write my own health indicators for things that don't come out of the box, just by implementing a very basic health indicator interface. Same thing from a traceability standpoint. Next to the health endpoint, we have an info endpoint that you throw some very basic plugins and properties into a Maven or a Gradle build, and you can automatically get, here's my Git commit information. Here's exactly what SHA, what branch, who did the commit, when did it happen. I can get Maven information. I can get any other thing that I implement an info extension point for. And then distributed tracing. This is a screenshot of Zipkin. And Zipkin's a tracing system that will accept telemetry from a bunch of services that are engaged in a particular request process. And those timestamps that we gather between when I've received a request and when I've serviced that request and when the client sends the request and when it receives the response are tagged with correlating information. To tag it with that correlating information, you need a tracer embedded in your application that's actually going to instrument those events. And so this is where Spring Cloud Sleuth can actually come into play. Just by adding that to the class path of my application, it will automatically start to instrument different flows inside of a Spring Boot app. So here are a few different examples. I'll post these slides after the talk so that you can get at these links a little bit more easily. But these are some different tools that Spring and then Pivotal Cloud Foundry, one of the interesting things that we've done there is we've taken our web console and detected, is an application a Spring Boot application? And if it is, we actually pull the information out of those Actuator endpoints and surface them in our application dashboard. And if you're not using Pivotal Cloud Foundry, there's actually a handful of open source dashboards out there that people have created that do essentially the same thing. So now that we have understood what we want to measure, and we've started to measure those things, we're going to need to build the software differently for those measurements to turn out the way that we want them to. And so we're going to need to start to leverage resiliency patterns. Cool thing about resiliency patterns, again, as they're mostly well characterized and understood, and also they're not that hard. In many cases, just the act of thinking about using these patterns and is going to make your system better because you're going to write your code differently. So we'll start really simply with just the notion of timeouts. Timeouts really matter when you're going outside of your zone of control. If I'm going to cross a network boundary, I can never assume, ever, that I'm actually going to get a response to the request that I send out. At some point, I have to be able to give up. And so again, thinking about timeouts is half the battle. I'm writing my code. I'm going to make a method call, and that method call is going to result in some distributed operation. And if I'm still building a system with threads as a concern, I'm still in a blocking scenario, and a lot of the stuff that I'm going to do for a while, even with all this reactive goodness that we're doing, it's going to have blocking scenarios. So, okay, is the thing that I'm going to do going to block a thread? Yes. Okay, it's going to block a thread. That means that if I wait forever, is that thread ever going to unblock? No. Okay, well, do we have an infinite supply of those things? How many threads do we have, right? Is it possible to run out? Yes. If we run out of threads, are we able to do more useful work? No. What might that mean? What might mean that clients of my service now are going to get into a similar scenario. If the clients of me are not thinking about timeouts, then they'll start to fill up and lose all of their threads. And we start to see this cascade across the system. So we need something to interrupt and get us out of trouble. If you're looking at an API, that you're using, some library that you've pulled in. You look at method calls. If you have a method call that has no timeout argument, and then you have another overloaded version of that method that has an optional timeout argument, always call the version that has the timeout argument. Why? Well, you might think, well, if it doesn't have a timeout argument, it will actually have a sensible default timeout. Probably not. Probably the default behavior is wait forever. Believe it or not, REST template in Spring delegates timeouts to the underlying request factory. The underlying request factory, if you're using the defaults, will actually wait forever. And so if you want REST template to ever actually time out, you have to go in when you create that bean and configure it with connect and read timeouts. Very simple to do. If you don't do it, just know that REST template's not going to save you when it comes to an HTTP request that never actually gets a response and holds an open connection. It will wait as long as you will let it wait. Retries. Sometimes we're going to have transient failures. We have a hiccup on the network, we send a request, that request would have gotten to an otherwise healthy service, we would have gotten a response back, or we have a system that is under load right now, we send a request, and it's overloaded at the moment, but if we had turned around and sent that request even a second later, that load would have gone down enough to be able to get a successful response. So sometimes just the simple act of, hey, a request failed, instead of giving up and popping an error up to the top of the stack, we just retry that request immediately. Sometimes that's going to be enough to get us going forward again. Now, don't take this to mean that, I should always retry every request that I send if it fails. You need to understand what are the systems that you're talking to and what is their behavior. Sometimes doing this is going to make things worse. Sometimes doing this is going to make things better. But when you're in the scenario where, I know that a system has reliability characteristics to where retries can be useful, we can throw this in. Sometimes we don't want to retry immediately. Sometimes we want to wait a little while, so back off some time. And we might retry again, we back off a little bit more. We could use a uniform back off, we could use an exponential back off, lots of different well-characterized algorithms that we can employ to do this. And then obviously we want to decide, when are we going to give up? Are we going to retry forever? Or are we going to retry only a certain number of times and then pop out and handle that behavior some other way? Regardless of what we're doing here, you really want to log all of these events. So I've had a failed request, I'm going to retry it. On the other side, obviously we're logging the request that we received and responded to, and then if we're correlating our logs with something like Spring Cloud Sleuth, being able to show, hey, we're having lots of retries here, what's going on the other side of that? And we can watch for those patterns and determine, is this just normal behavior, or is there something that we need to re-architect on either the client side or on the server side of this to be able to improve that behavior? Now, there's a little-known project called Spring Retry that makes this really easy to do. So, two annotations to point out here. The first method is annotated with @retryable. @retryable will give me a very basic, immediate retry with a uniform backoff strategy. Actually, no backoff strategy, and a maximum of like 3 retries. And if that's good enough, you've got that. And then the next method is annotated @recover. And so for this bean, anytime one of these @retryables actually falls out and has a maximum number of recoveries, then we can actually execute this method instead. And so this is a very simple example of retry our request for some things for a few times, and then if we can't ever get it, then actually give just some default response. Now, if we want to introduce a back-off strategy, that's pretty easy as well. So retryable takes a back-off argument, and we can hand to it another @backoff annotation where we can enhance the behavior by adding delays. What do we want to start with? What do we want the maximum to be? What multiplier do we want to use between them? Do we want to randomize that backoff in any way? I want to move away from a uniform distribution backoff strategy to an exponential backoff strategy. I can simply add a bean of type backoff policy, and there are several of these provided in the library. One of those is exponential backoff. You simply declare this bean, and then all of your retries are going to become exponential backoff-based retries. Bulkheads. So we take ships and we divide them up into watertight compartments with these walls that we call bulkheads. Why do we do that? Well, if we get a hole in the ship and we don't have bulkheads, then the whole ship can fill up with water. If we have bulkheads with watertight compartments, we get a hole in the ship. There's a limit to the scope that's going to fill up with water, and that can give us a greater chance of survival. That can give us a greater chance of being able to contain and fix the damage before we lose the ship. So we can translate this idea into our systems. How do we divide our system up into watertight compartments? Well, one of the ways that we think about doing that is microservices. By dividing our systems that have different types of failure modes and picking those failure modes that we want to isolate and putting them into different services, then we can build bulkheads into the system architecture. Now, you know that this comes with, once I've isolated that failure that way, I have to deal with the other failures that come along with being a microservices distributed system. So none of this is free. If we're within, again, a single application that's dealing with threads, again, dividing different types of work into different thread pools so that if one of those types of work becomes sick or behaving badly, there's a limit to the number of threads that it actually can consume from the system, so maybe other parts of the system can continue behaving normally. And if you're using Hystrix, which is actually most famous for being an implementation of the circuit breaker pattern that we'll talk about next, it also actually implements thread pool bulkheading out of the box. We can zoom back out of the architecture and think about the notion of availability zones. So if we're using a cloud provider or we're using multiple data centers, we can actually deploy our application across multiple availability zones. And so that if we lose a data center, if we lose an AZ in the cloud, we can have some understanding that that failure is going to be isolated from the rest of our application, and our application can continue behaving normally. And finally, the circuit breaker pattern. Circuit breakers are, again, really simple. And that's where a lot of their power comes from. It's a very basic three-state state machine. Requests are going to pass through a closed circuit just like electricity passes through a closed circuit. When our circuit breaker is in the closed state, so we put this circuit breaker between my client and my service, closed state, requests just pass on through. If we get a failure of any type, so an error, we get a timeout, then we're going to count that, and we're going to look at the number of failures that we have in a specific threshold of time, and once we hit that threshold, we're going to trip the breaker, and that lands us in what's called the open state. Open state, open circuit, electricity doesn't pass through. Open circuit breaker, in software, requests are not going to pass through. Meaning that we're never going to talk to the other service in this state. We're going to say, that thing is sick, so I'm not even going to issue the request. Instead, I'm going to fail immediately and leave it to the system to decide what to do with that failure. And circuit breaker library like Hystrix gives you built-in abilities to define a fallback behavior to go along with that open circuit. Now, if this is where the state machine stopped, even if that downstream system became healthy again, we would never talk to it, we would never know. And so the way we break out of that open state is by periodically transitioning into this half-open state. And in the half-open state, we behave just like the closed state, except when a request comes in, we're going to process one. We're going to send that request to the downstream system. If it succeeds, then we're going to transition back to closed and go back to normal. If that canary request that we just sent out fails, then we're going to go back to open. And so we'll kind of oscillate between open and half open while we're waiting on health of our downstream service to come back, and then we'll go back to closed. So if you're using Spring Cloud, bringing circuit breakers through Hystrix into your application, again, pretty simple out of the gate. I can annotate any bean method with @Hystrix command, and I now have a default configuration circuit breaker wrapped around that behavior. Passing to it the argument fallback method, just like with Spring Retry where we had the @recover, here we're going to give it a method argument to say, call this method when this circuit breaker is open or when we experience any failure in a closed circuit. Of course, we can tweak all of those thresholds and counts that I talked about by passing additional arguments to the Hystrix command annotation. So again, take a look at Spring Retry, take a look at Hystrix, or you can leverage Hystrix directly or go through Spring Cloud to get this annotation of Spring Bean behavior. Okay, so last point, embrace chaos. We've measured all the things. We've used all the resiliency patterns. Our system is resilient now. Yes? No? Maybe? We don't know. How do you know your system's going to tolerate failure if it hasn't failed yet? We want to actually practice failure. If you think about recovery exercises, if you think about disaster, do you want to learn your disaster recovery procedure in the disaster? Or do you want to learn it before so that you're prepared? So one of the simplest things that you can do is what's called game day exercises. If you think about sports teams, they practice so that when they're in a game situation, they can go off muscle memory and not have to be thinking about, well, how do we actually play this game? So we can put a date on the calendar to say, I'm going to simulate a catastrophic event, and we're going to practice our response. And we're going to evaluate both our system's ability to respond as well as the people who maintain the system. It's kind of hard to separate the software from the people who created and maintain the software. So we're going to evaluate our ability to respond. We're getting crosstalk.
Please welcome to the stage one of the world's best software developers.
Thank you. So you don't want to evaluate your emergency readiness in an actual emergency. But game day exercises maybe aren't enough. So Yao and Chung wrote this paper in 1975 called The Design of Self-Checking Software. And in the paper, they made this pretty audacious proposal that we should insert fake ghost planes into an air traffic control system. And the premise was that if the air traffic controllers could land all of the ghost planes and all of the real planes, they don't know what they're talking to, then we can actually trust that system. Now, this was never actually implemented, but these ideas kind of percolated and eventually turned into things like the Chaos Monkey. Chaos Monkey gives us the notion of an unscheduled, random game day exercise. We run processes that will kill things randomly and run that during the normal business day. while we're working and actually simulating failures. And we know that when we build a service, our service is going to have to withstand this type of chaos, which means that we build better software. We build more resilient software. We get better at handling and responding to failure. And ultimately, all of this contributes to make the system better. I want to show you one of these two examples from the Cloud Foundry space. So we're going to look at two microservices protected by a circuit breaker. I'm going to use Siege to generate load on the client microservice. We're going to look at the log tail on the backend service, and then we're going to create chaos events with this module from the Cloud Foundry ecosystem called Chaos Loris. So top left pane is our load generation, top right pane is our logs, and this video is like way far ahead of where it should be. Let me bring that back to normal. Okay, cool. And we've got a circuit breaker that we're monitoring over there to the left. So what I'm going to do is I'm going to post some things to the Chaos Loris API. I'm going to give the Chaos Loris a handle to the application that we're talking about. And so now Chaos Loris knows about my app. I'm now going to create a schedule. I'm going to run chaos every 15 seconds. You probably don't actually want to do that in production, but this is a demo. I can do anything I want. And now we're going to create a chaos event that ties that application and that schedule together with a percentage of times that we should end up killing that downstream service. So now we're going to watch the logs on the Chaos Loris, and it's going to start telling us every time that the chaos schedule actually runs. So we've started it up, and we're going to start to get some chaos events. So we'll speed up time a little bit here to make things not so painful to wait on. And eventually, we're going to get a chaos event that actually is going to shut down the downstream service. So we got that right here. We see that we're going to terminate the application. We look at the logs for the application. It says, okay, we've successfully destroyed the container that application's running in. We watch the circuit breaker. We see the circuit breaker go unhealthy and trip to open. And so now we wait. Now Cloud Foundry is going to automatically recover that application that it determined is no longer healthy. And it's done that. The funny thing is while that happens, Chaos Loris strikes again and shuts it down while it's trying to recover. And so we end up actually having to wade through a couple of these failure events before our application comes back to healthy again. And this actually turns out to be a really good example of reality as opposed to kind of an imagination, kind of a fantasy system. Like, are we always going to successfully recover immediately, or are we going to potentially go through a few different failure scenarios before we do? And so this randomness to the chaos can actually help us to get really good at handling these types of events. Okay, so let's make sure we understand where we've been. Stop trying to prevent mistakes. Embrace failure. Focus on mean time to recovery. Make failure cheap. Make recovery fast. Make sure you know what you need to measure to understand that your system's healthy, and measure those things. And make sure that your architecture enhances your ability to see. Learn these resiliency patterns and leverage them where they make sense. And then embrace chaos. Start to practice failure continually so that you can actually make your software better. I think we've got 15 seconds. One quick question. All right, I don't see any hands. Thanks very much.